Good. Excellent thinking. And yes, this, and this. Okay. Hello again, everyone. I'm sorry for starting a little bit late. Fortunately, camera is working now, and it seems that we just need to unplug it. Okay, so we have last week we reviewed a little bit about the concepts that we had in statistics. This week we want to use these concepts and we want to see a new type of running time. We have seen worst case running time, we solved some problems, you have seen it in Foundation 1 also, and also in this class we reviewed the concept of worst case running time and we have seen some examples. So this semester, more precisely this week and part of our class next week, we want to introduce a new type of running time, which is called expected running time. To find expected running time, we need to use some concepts of statistics. We reviewed very quickly concept of sample space, probability measure, and random variable. We explained about random variables. And I believe that we have seen one example about Bernoulli distribution. As we explained, Bernoulli distribution is a distribution that has two outcomes. One of them is considered as failure, another is considered as success. And if you assume that the probability of x equal 1, x equal 1 means that the probability of success is p, the probability of x equal 0 means the probability of failure is 1 minus p. And then we have seen one example. For example, if you flip a coin, two cases can happen. You can have head, you can have tails. Then for something like this, we will use this notation, coin flip. Coin flip means outcome of flipping a coin. You can have coin which is fair, you can have coin which is not fair. If you have a coin which is fair, probability of head and tail are the same. Both are equal to 1/2. If the coin is not fair, probability of head and tail are different. Okay, so and also we explained about uniform random variable. As we explained, uniform random variable means the sample space. That probability of every element in the sample space is the same. That's the concept of the uniform random variable. And then we explain about this notation that we will use it a lot this semester. When you have random k, means you have the sample space with k outcomes, and the probability of each outcome is the same. See? Probability of each outcome is the same. Probability of S1, S2 go to Sk are the same. All of them are 1/k. Okay, so these are notations and concepts that we had on Friday. Any questions, any comments, anything? Perfect. So then, what is our main goal this semester? For this chapter that we are starting today, our main goal is use the concept of expectation from statistics. Then let's first see what expectation is. This formula may be scary. You have seen it in calculus, but if you forget it, it's okay. Let me tell you what expectation means. Forget about formulas, forget about this concept, formulas that we had in statistics. I'm sure that you may remember in statistics, by using integral, you can find expectation, very tricky formula. But what expectation is? Listen to me very carefully. Probability theory makes sense when there is some uncertainty. If there are no uncertainty, means everything is certain, probability doesn't make sense. I gave you a funny example. See, in my country, election is not an example of experimental, which is called uncertain. Why? Because 2 years before election, everybody knows that who will win. There will not be certain. Let's be very much. Perfect. So, but in some countries that election has uncertainty, probability makes sense. It means in my country, if somebody asks me, what is the probability that you win the election? 0, absolutely 0. Because winner is known. Nothing is uncertain, everything is certain. Everybody knows who is the winner. Therefore, nothing is uncertain. Probability here doesn't make sense. This kind of experiments in mathematics, there are two kinds of experiments. We have a stochastic experiment. A stochastic experiment means experiment for those uncertainties there. And in my country, election is not a stochastic. Why? Because outcome is known. Outcome is everybody knows before election, 2 years before election. Okay, if we have the sample space with some uncertainty, like election here, that before election you don't know who will win, approximately. Okay, so for situations like this, expectation has a meaning. Expectation means what outcome has more chance. For example, if you have an election with two candidates, you can talk about your expectation to say that you think which candidate has the higher chance. Your expectation about, for example, candidate number 1 is what? If I ask you what candidate you expect to win, which candidate you think has the higher chance? You see what I'm saying? In my country, this question doesn't make sense. Because expectation doesn't make sense. When you know who is the winner before election, what does it mean if I ask you who you think will win? Everybody knows. Nothing is a stochastical. Everybody knows who will win. But if we do not know who will win before election, then expectation makes sense. Historically, the concept of probability was established by gamblers. I know that maybe it's funny, but it is true. Because suppose you go to Vegas, okay? You want to know that if you play a card, you want to know that which outcome has the higher chance. Historically, gamblers were looking for finding someone who can tell us if chance has the mathematics concept behind it or not. You see what I'm saying? That's exactly something which happened historically. Several years ago, I applied for a job, and the job was in casino in Vegas. They were hiring mathematicians. Very good salary, actually. Why they are hiring mathematicians? Why a casino hire mathematicians? Because they need mathematicians for help them to get your money. That's exactly something that they do. As a mathematician, I can tell you, if you go to casino, never, ever, ever, ever play with machines, because definitely you will lose. Definitely. In machine, they are adjusted in a way that you lose. Definitely. But, you know, you guys know Woody Allen? Woody Allen? Woody Allen? No? Nobody go to cinema? Woody Allen is a very, very famous director, American director. He has something funny. He says that if you go to casino and you lose your money, it doesn't mean that you do not have a good time. You had a good time and you lose your money, then you everything is life is balanced. He's a very nice guy, actually, very, very nice guy. He's one of my favorites. Okay, so then why they are hiring mathematicians? And they offer me a very good job. Why? Because mathematicians help them to get people money. That's exactly something that we do in probability theory. Whatever that we have in probability theory is discovering mathematical meaning of chance. That's it. Then always probability theory makes sense if chance has a meaning. It is if outcome doesn't know, chance has a meaning. Now, mathematically, our expectation is denoted by this notation and it's called expected value. And expected value means our expectation. Now let me tell you about this horrible formula. What this horrible formula is telling us? This horrible formula is not something horrible. This is an average formula. That's it. When you want to find average of 10 numbers, what you will do? You will add 10 of them, divide by 10. That's exactly the same. But what's the difference between this and average formula? In average, you assume that the weight of every number is the same. But here you are assuming that the weight of every number is not necessarily the same. Then what this formula is telling us, if chance of everything is the same, mathematics tells us if you want to bet, it's better to bet on the average. That's what we are saying. This is one example. Then if you For example, for the experiment of tossing a two coin or coin two times, mathematically they are the same, we let x represent the number of heads. We have the following probability. See, x shows the number of heads. Each one means two tails, one head, one tail, or one tail, one head, and this guy, two heads. Probabilities are given. We want to find expected value. That's the expected value. See, I will multiply each outcome by its probability. That's exactly something that you do for taking average. The only difference is that the average that we usually use has one assumption. Assumption is that the probability of everything is the same. But here, as you can see, probability of elements that we have are different. You will calculate this, then you will get one. What does it mean? It means if you flip two coins, mathematics tells you the chance of having one head is higher than other. It doesn't mean that every time that you flip two coins, exactly one head occurs. It means that if you continue flipping two coins and you write the number of times that one head occurs, you can see that the number of times that one head occurs is higher. Therefore, mathematics tells you if you go to Vegas and want to play with two coins, bet on the case that one head occurs. But if you go to Vegas and you fail, then I am sorry. Any questions? Any comments? Yes, please. I believe so, yes. In the previous week. Hmm? Yes? Really? Let me check in. See that if I didn't post it, shame on me. I'll do it right now. Sorry, modules. So I click on modules. In the previous week, no, expected analysis is posted, but that one was not posted. Shame on me. Sorry about that. Let me post it the new week. Sorry and thank you. Assignment on this. That was strange. Okay, it should be there now. Thank you for telling me. Sorry that I thought I did, but it seems I didn't.
Yeah, I can see it now.
Sorry. No, thank you. Okay, so okay, that's it for statistics. It's enough, and we may need one more formula. It is on the slide. We will come back to that formula again. But now let's see in what way we want to use this horrible stuff that we had in statistics. Our main goal, this concept first, before starting, I should say that this concept is a very tricky concept. In Foundation 2, we will cover two tricky concepts. One of them is this probabilistic analysis. That's a very tricky concept. Why this is a tricky concept? Because we are using several concepts. We use for analysis, if analysis and recursion that we had in Foundation 1, and statistics. Then you can see that when you have a combination of different tricky concepts, then this concept also should be tricky. We will cover this concept, I think, in at least 3 lectures, or maybe 4, then 2.5 for this week, 1 lecture next week, or maybe 2 lectures next week. And the second tricky concept that we have in Foundation 2 is the concept of anti-completeness that we have at the end of the semester. It's a very theoretical concept. So then this concept that we are starting today officially is the first concept that we have for Foundation 2. So let's see what we want to do in this chapter. So let's start by one example, hiring problem. That's a funny and nice example. Suppose that we need to hire a new office assistant, and we decided to use the employment agency. Then suppose we want to hire a new employee, and in order to hire a new employee, we want to use employment agency. So the employment agency send us one candidate each day. It means every day, this agency send us one candidate. We interview this candidate and then decide either to hire this person or not. And the process is very usual procedure. You must pay the employment agency a small fee to interview an applicant. It means that every applicant that they send us is not free. They will charge us, but we need to pay a few fee, okay? And you decide that after interviewing, you decide if applicant is better qualified than the current office assistants, you will fire the current office assistants and hire the new candidate, okay? So you are willing to pay the resulting price of this strategy, but you wish to estimate what that price will be. That's our goal. I want to explain about one thing first. Suppose they send us n candidates. We do not want to stop interviewing. We want to interview all of these n candidates. It means that they want to send us this agency, they want to send us n candidates, but we do not want to stop interviewing. When I'm saying that stopping interviewing means that suppose, for example, they interview me and they decide to hire me, but they do not stop interviewing because they think that there is a chance that, for example, the next candidate that comes tomorrow is better than me. But the process is like this. They interview each person, but when they decide to hire me, they hire me. But they interview the next candidate tomorrow. If the next candidate, which is being interviewed tomorrow, is better than me, they fire me and they hire the guy. Funny, no? That's what we do. It means if they decide to, for example, hire me, they do not say, okay, let's interview all candidates, then among them we choose the best. No. Every candidate which is interviewed, if they feel this guy is better qualified than the current office assistants, they will definitely hire this guy, and tomorrow again they will interview another candidate. If the next candidate who comes tomorrow is better than me, they fire me, they hire the guy, and they continue. Makes sense? Makes sense? Procedure makes sense? A little bit funny, but okay. Makes sense? Makes sense? Okay. So, now let's see. Let's make it a little bit more mathematical. Assume that candidates for the office job are numbered 1 through n. And we have this algorithm. Let's see. We assign best is a variable. We assign 0 to the best. We are running the for loop, I to 1 to n. We interview candidate I, and we compare candidate I if candidate I is better than the best candidate. Best here means this variable best. We compare best and I. If I is better than best, we update best to I, and we hire candidate I, and we continue. Okay? So, please remember that when you hire the guy, you should pay, and when a guy is coming for interview, also you should pay. Here we have then 2 fees. Number 1, interviewing has a low cost. Say CI, I stands for interview. Whereas hiring is more expensive. Costing, say CH. Then see you have 2 fees. 1 fee for hiring, 1 fee for interviewing. Everybody will be interviewed, but some candidates will be hired. See, everybody will be interviewed, but some candidates will be hired. Then we have the cost for interviewing and cost for hiring. Cost for hiring won't be paid for everyone, but cost for interview will be paid for everyone. So then in general, you can say that's the cost that you may have. Or n of CI plus m of CH. You have n candidates, everybody will be interviewed. Then there are n candidates who will be interviewed. Then we have n CI. But m of them, m is less than or equal to n. M of these people will be hired. Then that's the cost that we have. So now we can ask this question: what is the worst case scenario? In what case, in what scenario is considered as worst case? In what scenario you will pay the maximum number of fees? Yes, we do.
You hire every single person.
We hire every single person. So what was the name again?
Tanner.
Tanner, in what scenario we will hire every person?
So every new person being interviewed is vetting them best.
Exactly. In what scenario we hire, as Tanner told us, in what scenario we hire everyone, that candidates come in the increasing order regarding to their qualification. Means, for example, the best candidate is terrible, the second one is a little bit better, the third one is a little bit better, the fourth one is a little bit better, the last one is the best. Then see, these people are sorted with respect to their qualification. And remember that in what scenario which happens, we will hire the first candidate, because the guy who is the current officer of his assistance, we hate the guy passionately, we want to get rid of the guy, we want to kick him off. And the first one definitely will be hired. But if we assume the second one is a little bit better than the first one, third one better than the second one, and go to the last one, then everyone will be hired. That's the worst case scenario. In the worst case, we actually hire every candidate, as Tanner told us. And this situation, that's important for us. This situation occurs if the candidates come in a strictly increasing order of quality, in which case we hire n times for total cost of hiring, we have CHN. Why CHN? Because when worst case occurs, N and M are equal. M is the number of people who are hired, N is the number of people who are interviewed. Then in the best case, M and N are the same. Then when N and M are the same, therefore we can simplify them and we get this. Why we have CH? Because remember that CH is much bigger than CR. The cost of interviewing is smaller than cost of hiring. Therefore, when N and M are equal, then since CH is bigger than CI, then CI gone and CH left. Okay. Any questions, comments? Hope up to know it makes sense. Questions, comments? That's the worst case running time of the algorithm that we had in the previous slide. We are comfortable with worst case running time, because in foundation one, we use worst case running time for almost all algorithms that we had. Some of you may have heard a little bit about average running time, but a little bit. I want to explain that why worst case doesn't give us a good expectation. Because as Candy told us, worst case for this problem occurs when candidate comes in the increasing order. In reality, how much it is possible to happen? In reality, it's hardly ever happen. Suppose n people are being invited for interview. In reality, the first guy is good, the second one is perfect, the third one is terrible, the fourth one is more terrible, the fifth one is very good. Then see, in reality, quality of people are distributed randomly. This is a very, very, very extreme assumption if you assume we have n people who are chosen randomly and their quality is strictly in increasing order. That's very strange. That's the reason that we need to find another running time, which is more realistic, because the worst case running time for this problem is too extreme. This is the word that you will hear from me a lot until end of this chapter. Worst case always occur based on very extreme assumptions. Same thing for best case. Worst case and best case occurs when you assume very extreme assumption. And we will see that expected running time is more realistic. What expected running time means? In order to perform a probabilistic analysis, we make assumptions about the distribution of the inputs. Then we analyze our algorithm. When I'm saying that when we make the assumption means that we assume that this extreme assumption that we assumed every person comes with increasing order, these n people who are being invited for interviewing are in the increasing order with respect to their quality. We assume that this assumption is not true. And we assume that the quality of these candidates are distributed randomly. If you assume that the quality of these people are distributed randomly, now we want to see that what is our expectation of costs that we need to see. Then see, listen to me very carefully. That's very important to understand. When I assume the quality of these candidates are distributed randomly, my goal is to find my expectation of the cost. Do you know why I am emphasizing on the word expectation? Because the real cost is not known. Why the real cost is not known? Because only God of these worlds know that before interviewing this candidate, in what way the quality of this candidate is distributed. Before interviewing, we don't know that, for example, candidate 1 is better than candidate 2. Therefore, we cannot have the real number, exact number about the cost. Then since we do not know the exact value, we will find our expectation. Means that we want to know that mathematically what number should be expected. If you understand this, you understand everything that you had in statistics. All the stuff that you were taught in statistics, forget about those horrible formulas that you had. That's the core of statistics. If you understand this, you understand everything. In statistics, you have variables which are not known. Why those variables are not known? Because they are chosen randomly. Then before finishing the experiment, we do not know what values will be chosen. Then because of this uncertainty, the exact value is not known. Then what we will do? We will find our expectation. That's exactly something that we do here, and that's exactly something that we did in the statistics, for all the statistics that you had. If you understand this chapter is like a drink in the water. If you do not understand this chapter is like in the garden in the middle of the desert. Then that's a very important concept. You understand this, you understand everything. Expectation means you are working with variables that are not known, therefore you will evaluate your expectation. That's the core of this chapter and core of statistics. Any questions, any comments, anything? I hope not going too fast. Any comments? Okay, so in order to approach to solving the problem that we have, means the hiring problem, my goal is to find my expectation of the fee that we need to pay. I need to give you a little bit math background. First, we will see a function. This function is called indicator function. What indicator function is? Suppose you have a sample space and you are choosing an event in the sample space. Indicator function, which is denoted by I of A, is defined in this way. If A occurs, indicator function shows us 1. If A doesn't occur, indicator function shows 0. Then indicator function means the function which gets 2 values, 1 and 0. When A occurs, 1. When A doesn't occur, 0. Very easy. We have one example here. For example, suppose you are flipping a fair coin. When I'm saying that fair coin means the probability of head and tail are the same. And then you define indicator function by I of h. What is indicator function? We consider indicator function for h means that if h occurs, this function shows us 1. If tail occurs, this function shows you 0. That's the expected, that's the random variable. You can find expected value of the random variable. When you want to find the expected value of the random variable, you will multiply probabilities by the values that this function can accept. This function will accept 0 and 1. 1 occurs when a head occurs, probability of head is 1/2. 0 occurs when tail occurs. Probability of tail also is 1/2. When you evaluate this, you will get 1/2. 1/2 is probability of head. Then expectation of this random variable that we define here is same as probability of head. So this is true for every case. It means if A is an event, if indicator function is used to define random variable, expectation of random variable is same as the probability of A. A little bit tricky, I understand, because as you can see, a little bit theoretical. So, but the only thing that we said, I remember the first time that I saw this, I was undergrad, and it was strange to me. Something that we are saying here is that if you use indicator function to define a random variable, then expectation of this random variable is same as probability of A. Okay, so let's see one example, because I don't want to make it too theoretical. It's a little bit theoretical. So let's see one example. Let the random variable x defined as the number of heads on the flip of a single coin n times. Then you have a coin, you are flipping this coin n times. We define x of I as indicator function for i's flip results in the event of h. What does it mean? It means xi shows us if the i's flip is a head or not. Means when you flip a coin, two scenarios can happen. Let me give you one example. It sounds a little bit too theoretical. Okay, so guys, see, suppose for example, you flip a coin, we flip a coin, say 8 times, for example. And we have 8 random variable, x1, x2, x3, x4, x5, x6, x7, lastly x8. And we have these values, 1, 1, 0, 0, 0, 1, 0, 1. We flip the coin 8 times, and we have these values, x1, 1, x2, 1, x3, 0, x4, 0, x5, 0, 6, 1, 7, 0, 8, 1. Okay. What these values are telling us? For example, if I ask you, what outcome we had when in the first head or tail? What outcome we had in the first head or tail? What do you think? I think definitely head, not probably. But why? This is head. How we define what? Oh. No. Here we did not talk about probability, but thank you for sharing with us. Better answer. Yes, the first flip is head. How do I know that?
Because x1 equals 1.
x1 equals 1. Because the meaning of x1 means outcome of the first flip. And since we define xi equal to I of h at i's flip, then here what you can say, then x1 is 1, means in the first flip, head occurs. What about the outcome of the second flip? Outcome of the second flip? The flip. Again, head, same reason. Then outcome of the third flip. Tail. Then here we can say that we have something like this. H, T, H stands for head, T stands for tail, then first field head, second field tail, third field tail, fourth field tail again, fifth tail, sixth head, seventh tail, eighth head. I didn't do anything complicated. The only thing that I did is using these xi's to show what happened in the first flip and in the what happened in each flip. In ice flip, if head occurs, we have 1. Tail occurs, 0. Any questions? Any comments? Any questions? Now suppose I will define a new random variable. Say x equal to number of heads. What is number of heads, guys? 4. Here we have 4 heads. And if we add all of these xi's, what happens? x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7 plus x8. Again, you get 4. Is it true always? Yes. What we can say, in general, we can write very helpful formula. This formula is used a lot. So, in general, we can say x equal to summation of I from 1 to if we have n flip, we can say x is the number of tails, the number of heads, heads is sum of x I from 1 to n. Any questions? It is a very famous formula, easy formula, but very famous. In reality, something that we are saying here is very easy. Then again, see, you hear from me and until the end of the semester a lot. Many concepts in mathematics are based on very easy stuff. But notation makes these concepts tricky. If you understand notation, you see that something that is behind the notation is very easy. Something that is behind the notation, you have bunch of zeros, bunch of ones. If you add a number by 0, nothing is changed, right? Suppose you have 1,000 plus million zeros. Million zeros which are added to a number doesn't change anything. Those zeros are the case that head doesn't occur. The only cases that you have 1, because xi does accept 0 and 1. 0 are for the case that you have tail. Million zeros, you don't care about those zeros. Ones matter. The number of times that you have 1 tells you the number of times that you have tail. That's what you have. Here we are saying that the number of times that we have 1 is same as the number of times that you have heads. So if you want to translate this, number of heads is number of times, number of flips, number of flips, that's a head. That's the only thing that we have in this formula. Very practical, helpful formula, but as you can see, it's based on very easy fact. Why it is helpful? Every formula which can be used to decompose a random variable into other random variables are very helpful. Why it is helpful? Because my main goal is to find the expectation of x. I mainly want to find expectation of x. Every formula that decomposes x into other random variables are helpful because you have a linear property for the expectation. Linear property for the expectation tells us expectation can be decomposed over some. And we will explain about this. Means that expectation of x expectation of x is sum of expectation of each xi. And expectation of each xi is nothing other than 1/2. Okay, so then let me show you this on the slide. No. Okay, so then here we can say x equal to sum of xi's as we explained. And if you want to find expectation, you just need to find expectation of each xi, then add them. Expectation of each xi, because you define xi by the indicator function of head, is 1/2, because it is same as probability of head. And probability of head is 1/2. And you are adding 1/2 n times, so here you will get n over 2. What this number means, I evaluated the number of times that I expect head occurs. Do you know what we have here? If you flip the coin n times, and if your coin is fair, means the probability of head and probability of tails are the same, your expectation of the number of times that head occurs and tails occurs are approximately the same. Means if you flip the coin 50 times, we expect 25 times head occurs, 25 times tail occurs. That's what we have here. Again, see, that is something very easy. If you have a fair coin, that is safe to say that when we flip 100 times, we expect we have 50 tail, 50 head. But see, when we write by notation, it looks strange. Again, if you understand notations, in many cases, you will see that something that you are explaining is very easy. It's very easy. Okay, hope this example makes sense and hope it was not very tricky. Questions, comments, anything? Okay, I want to recall you one concept from statistics and from Foundation 2, Foundation 1. And maybe some of you have seen this before in Calc 1 or Calc 2, mostly Calc 2. This sum is an important sum for us, which is called harmonic sum. Harmonic sum means that you are adding 1 plus 1/2 plus 1/3 plus 1/4 go to the 1n. That's the sigma notation of this harmonic sum. Why harmonic sum is important for us? This formula. Harmonic sum can be bounded from top by log of n. This formula is an easy formula if you are familiar with the statistics, with calculus and the concept of Riemannian sum comes directly from Riemannian sum. That's the Riemannian sum, and that's the integral of 1n. And we took integral of 1x and we got log of n. Then that's very easy. But if you are not familiar with those stuff, then it's okay. The only thing that you need to memorize is this formula. That asymptotically, harmonic sum is same as log of n. If I want to recall you one concept from statistics, that's something that usually we have in calculus and in statistics course. In calculus, we explain in this way. Harmonic sum is divergent. It approaches to infinity. But this infinity is not very strong infinity. Why? Because it is same as log of n. As you may remember from Foundation 1 and this semester, at the beginning of the semester, we explained logarithm at infinity is not very strong, powerful infinity. Then here, that's something that we are saying in this formula. That harmonic sum at infinity is infinity, but this infinity is a skinny infinity. That's a very fat infinity. That's skinny infinity. Okay, so this is one review from concept of harmonic sum. Oh, okay. I just want to advertise of what we want to do on Wednesday, then because we need more time. Our goal on Wednesday is to find our expectation for the number of people that we will hire. And see, my goal is to compute the expected number of times that we hire a new office assistant. We come back to the hiring problem. One more time, please remember, we do not, why the word expected here makes sense? Because we do not know what is the exact number of people who will be hired. Because people, candidates, come in the random in the random distribution, means that we distributed these people randomly. Then we do not know which candidate is better qualified than other, because before interview it is not known. Then we do not know how many people will be hired. Since this number is not known, then what we will do, we will find our expectation. That's what we want. Okay. The only thing that I want to recall you, please remember that the worst case running time of this procedure for hiring the office assistant manager was O of n. And we want to find our expectation. And as we explained, our expectation should be based on randomness. When you assume these people come randomly, then your expectation of the number of people that who will hire is more realistic, is more accurate. Because as we explained, worst case running time is based on very extreme assumption. Okay, so I think it is good time to stop because we need much more time to explain about this. Any questions, any comments on here? We will continue on Wednesday. Have a good day, guys, and again, any questions, please stay.